We would have to figure something else out. We're live? Okay, good. Now I hit play. Oh, how do we go backwards? Okay. Something's happening.
It is happening.
Do you think it may switch to whatever I'm doing? Oh, yes, there it goes. Now it's back.
Cool.
We have a thing.
We're live.
How do I make the clock stop, though? I want to make my clock stop. Or else, how do I know my timing?
No, you can start and restart it.
That's what I'm going to do. And as long as you don't touch it, then the clock stays. Okay.
Cool.
So, are there more than 10 people that are going to be watching this?
So instead, 3 are watching now.
Well, that's one is you. Okay, so 2 more. Okay, I'm down with that. No, I'm just only because I mean, the talk is 2 weeks from now.
Yeah.
So the level, I would consider this a draft.
Right.
So the presentation quality will be of a draft. So I'm supposed to finish in 18 minutes. When I practiced this morning, I was at 20. When I practiced next time, I was at 19. So I'm not far.
No.
But as long as the audience online is not going to throw tomatoes at me.
I don't know if they all know it's for Sigma.
Oh, okay.
So I don't know if they know.
They might get it in the footer. I put it in the footer of every slide.
Ah.
Which you won't see on this slide. It's not on this slide. This is a title slide. You can't have those things.
No.
All right, so we are cooking with gas. Okay. So now we have 7 minutes to kind of wait.
Yeah.
All right. Okay. I will think about. I have nothing to think about, so we'll be fine. The primary author of this paper couldn't make it today. One of his kids has a recital this afternoon, and he's leaving for Amsterdam early because he's taking his family to Europe at the same time. So I wanted to call him out more and be like, by the way, if I don't know something today, Ming Chuan's the person you need to talk to. And the 2 primary authors of the paper are not here today. Ming Chuan and Sandeep wrote the vast majority of the paper. I wrote a little bit, and then Mudp and Caillou helped edit the paper. And so anyway, it'll be fine. It's going to be fine. I'm going to say some words. They might make sense. They might not. It'll be okay.
Yeah, YouTube forever.
That is even better about it. No, I have other talks on YouTube. So I guess the question I have, here's one thing to verify. Is the audio actually working the way you expect? So I don't know if maybe it makes sense that I stand here and continue babbling and can you hear what I'm saying and it sounds okay?
Yeah. I think it's okay.
All right. Oh, and you just see the slides.
Yes.
So they won't see me, which is fine. Okay. I wasn't sure because the webcam's off, so it won't see me. All right, cool.
Great.
Good.
Yeah. 2 watching now.
Well, they're like, it hasn't started yet. So.
We'll come back later.
Oh, boy.
Is this your group's first presentation at Sigma?
Yes.
Okay.
No, even more significant than that. This is my first presentation at an academic conference. So one of the things that I have to be careful of is I've presented at trade shows a lot. Trade show talks are sales talks. And so I have to, I want to make sure that I maintain a neutral voice and not try and sell what we've done.
That makes sense.
Yeah, it is all up and running.
That's why you know we had money.
That's why.
And she was talking recent, and we had a lot of PhD students because he could
touch stuff, yes.
I think we can actually get them.
This worked. This will be my first live YouTube presentation. I have never done that before.
What's your position? Because I need to introduce you. So Rajat
Aria is
Yeah.
the correct name to pronounce it.
Yep. Yeah, it's great.
From Apple.
From Apple, and I'm an engineering manager
Engineering
in
manager.
the machine learning platform team.
Okay. That's probably as much as I can remember. This is great. And you'll be talking about your upcoming Sigma paper,
Correct.
which is really exciting.
And that's the title of the paper.
Yes, yes, yes.
The thing that's also, it was fun for the team today, is like, we have an internal name for it, but I can't share that. And so we had to rename it. So it's rebranded in the paper, and
Yeah.
we're not very creative at that. So the rebranded project name is MLdp, which is like,
Yeah, MLdp. Yeah. A GPU for data platform.
so like we just, so that's what we're saying about the team.
MLdp, which is nice. It's always hard to have good names. We always struggle. We're like not the. That's not part of our type of creativity.
I think the saying we say is it's the hardest problem in computer science is naming something.
Because we are computer scientists. For other people, that's easy.
I guess. I tend to think, I mean, yes, we come up with a lot of names. None of them are, no one likes, none are universally liked.
That's why we end up with like gods, goddesses, or because we just can't come up with it. But you need some artists. So I have some artists in my family, and their brain just works completely differently. Like for them, coming up with a name, drawing, it's just like easy. Like,
Not me.
but things they do like hangs like very like it's amazing looking, but it's not perfect.
Yep. Yeah, totally.
And then I decided I can actually classify people into artists and artists just based on how they play with children. Because I was seeing different members of my family play with my kids when they were young. There's a clear divide. I can tell. Engineer, not artist. And I concluded artists should be preschool teachers because the engineers way more. Because the preschool teachers, they're like,
Yes,
give me an
yes.
idea. So but I think the kids much better.
So one thing, we're actually broadcasting right now. FYI. We are. I don't know if you want to reset it to 4:30. I don't know. No, fine. Let's not do that. Because it's already running. It's not that. Right? That's the main thing. No, it's fine. I mean, we don't have to cut that out. I was just letting you know that we're just talking about things. But yeah, we were. Mute. Yeah, we can see it that way. That's probably easier.
And I went there and
So
I had like a maid that was there. I actually really loved meeting with students and talking with professors and talking about their work and giving them like advice, even though it was advice, but like you know, and then I actually really enjoyed. We're still looking for the interview experience. I was surprised at how much I enjoyed it. And kind of see myself like continuing to do that because it's such a like.
You can do two full, like, you can have two things for you.
In that, like, this way, I've been talking to some of these postdocs, they're ending, right, like, there were very few people who were taking just Chris students. It's like student, you know, like, and I was like, well, you know, it's a very different, hi. Dead silence, and I'm just talking out, like, oh, shut up. None of that. Probably doesn't keep
I already removed my access. So.
Really? Really?
Yeah.
Really? Oh no. I bet you can get a, I mean, if you care enough, you can probably get a card from the front office that's like.
No, just cut off.
Well, I mean,
Overdid it.
oh. Well, you should kind of decide where you're going.
Yeah.
Where you going?
I think I'm going to my year in Argoland.
Oh, congratulations. So she'll also get some graduation, so we'll be joining the CSB as a professor. And, we'll 1 year to start. Well, Shubo, if you want to be roommates, let me know. I'm just kidding. Because I'm in California and it's like really expensive there. And
That would be far, like a 5 hours drive.
I'll let you do the driving. I'll let you do the driving. You'll have to leave at like 2 in the morning. That'd be great.
What's the startup you're gonna be at first?
Algoland. It's a blockchain company. Do MIT people in Boston. So I'll be in Boston at least for 1 year. How do you spell that? ALGORAN.
Algo ran.
Yeah,
Cool. Don't tell us all about it now. Don't tell us all about it.
yeah.
All right, so let's get started.
All right, everyone. So welcome to this talk. We're super happy to have with us today a team from Apple. And Rajat Arya is the engineering manager, and he will be talking about a very cool system they have been building, and that is also going to appear as a SIGMOD paper very shortly on data platforms for machine learning. So thank you for being here.
Thank you. All right. Hi, everyone. Thanks for attending on a Friday afternoon. Again, my name is Rajat Arya, and I'll be presenting some work that we started about 2 years ago when we embarked on building a data platform for machine learning. And what I'll be presenting today is work that many of us have worked on. The folks' names in bold are with me today at SIGMOD, or will be in a couple weeks when I present this at SIGMOD. So please come and meet them to find out more. So why did we go about building a data platform for machine learning? Well, as you know, machine learning is everywhere, and its reach is only growing. And as you're familiar with, the machine learning lifecycle is a highly iterative one. But what we've realized in working with machine learning teams over the last few years at Apple, it's not the overall lifecycle that's making machine learning innovation, or that's slowing down machine learning innovation. It's the early stages of the machine learning lifecycle, the exploration, experimentation, and evaluation phases. And it's really how quickly can you get through these early phases over and over again that is driving new innovations. So it's the idea of how quickly can I figure out if this idea has promise before investing more time in it. So what can we do to make the early stage of the machine learning lifecycle more productive, increase the productivity for machine learning engineers? So we went to explore existing solutions. And the first thing we realized is one of the key pieces of machine learning is the actual frameworks that train ML models. Well, it turns out there isn't a few of them like I've listed here, there's dozens of them. And they're in active development, and in a large organization like Apple, every single one is in use. So we realized that there's no way that you could bind or build a solution for only one or two of these frameworks. You need to make sure that your solution is agnostic to the machine learning framework. So then we thought, okay, this is about model training. What about the rest of the stages in the life cycle? So we went looking at some of the platforms that were out there. And what we found is some of them said, bring your own data source, bring your own data system. But most of them just ignored the data component altogether and said, use the existing passive stores that you already have. We'll focus on the other parts of the life cycle: experimentation, evaluation, and deployment. So if we expand out the life cycle to some more stages than just the early stages, you see we have exploration, annotation, feature engineering, experimentation, and evaluation. And what we found is at each one of these stages, there's just some sets of storage, passive storage systems that were being used. And so these silos that are created, these data silos at each of these stages, might be okay in some domains, but this is especially problematic in machine learning. And that's partially because of the data that you use for ML. So the data itself needs to be an interface in machine learning to ensure reproducibility of your experiments. For most machine learning, the data is sensitive. So all the systems involved need to provide strong guarantees around privacy, security, and data retention. And the data is expensive to acquire, to curate, to store, to transfer, and to manage. And so if you have to do this over and over again through each of the silos throughout your life cycle, it increases the risk and slows down the work. And what we found is, because there are so many silos in place, the teams, the machine learning teams, were responsible for had the burden of integrating with all of these silos, and that was slowing them down. And of course, when you have data copied and transferred to all these different places, it increases your compliance risk. That, am I actually deleting all the data I'm supposed to? Am I using it appropriately, etc. And as many of you know, the machine learning community thrives on collaboration. So it's absolutely critical that teams can share their work and find relevant data to the project. And this is an important piece for the machine learning projects, especially where one data set can be used by many teams for many different contexts. And given how expensive it is to get a data set and to curate it, it's essential that teams can share this. And all of this motivated us to see that we needed an integrated data platform to support machine learning. And so that's what we've been working on. And we call our platform MLdp. So if we go back to this workflow with these stages, MLdp throws itself into the middle and provides a tailored solution for each of the stages in the machine learning lifecycle. So what this means is when you're in the early stage of annotation and exploration, you want a transactional system that you can interact with quickly that makes it easy for you to make changes, augmentations, or explore your data. But in the later stages, when you're doing feature engineering, experimentation, and evaluation, you want a system that scales well and is optimized for reads. And so that's the mindset that we've brought into MLdp. So today, let's go through the system architecture and walk you through the parts that we have in the system. So we'll start by looking at the data model, how data is represented in MLdp, and how you start interacting with the data through our domain-specific language or programmatic interface. Then we'll talk about how we store data in MLdp, and finally, how we access data in MLdp. So as we go through these parts of the system, I think it's good to go with to work through an example. So let's wear our machine learning engineer hats. And today, the project is to train a flower classifier. So what does that mean? What that means is I want to train a machine learning model that, given a picture of a flower, can predict what type of flower it is. So I'm training a classifier that can classify the name of a flower based on an image of it. So to train one of these, I need pictures of flowers, which we have here, and I need labels so that I can train. This is a supervised machine learning task, so I can train my model. So I'd also want to separate my data. So I have a training set and an evaluation set. So that way I can see how well my model is generalized or generalizing based on what I've trained it with. So this might be the typical way that a data set is organized for machine learning. And there's some parts of this that make sense. You have a table and you have files. This makes sense. But there's other parts of this organization that are limitations to the machine learning lifecycle. One, your training and test partition is fixed. So I have to copy the data if I want to change how which examples I'm using for training. The labels are part of the data. This is really problematic because that means another team may want different labels for the same data. They have to copy the data. And I don't know what version this data is. I don't know if someone's going to change it out from under me. I don't know if I train today, tomorrow if I try and use this data set, will I get the same results? And so let's look at how this data set is how we would handle this data set in MLdp. Our conceptual data model starts with a data set object. And so here you see we have the same images, and we also have a table. Then we normalize the labels into a second object, which we call an annotation object with a foreign key relationship to the table on the data set. And then we take the partitions and we create them as, you can think of this as query results materialized into a split object. And so now we've normalized our data set into the data set and annotation object, and we've introduced a split object.
I have a question. Why do you call these objects? Because isn't it that you have a table, and two views?
It's a good question. I think I'm thinking of them as objects because of the programmatic interface to using them. You could think of them as concepts in a way, that these are abstractions in our system. The next couple slides, I'll talk about how we actually store them. And so that they are tables, but they are also raw files. And so that's why I think of them as sort of objects. So it's not just, it's not entirely just structured data. So yeah, great question. So, so with this organization of our data, what we're able to do is provide a lot more flexibility for this data set without sacrificing any of the ease of use. Is that a question? Yes, it's a set of tables is the way to think of it. So you have a training table and a test table, and all you have are the IDs. So you can think of any filter that you could do on your data set. So, so imagine my data set has other columns as well. So in this example, I just have the ID and the file name, but I could have lots of other metadata as well. Anything I can filter on. So I could say, oh, well, I have a corpus of text, for example. I want English as a split. I want Chinese as a split. I want Japanese as a split. Does that make sense? Yeah. So it's a set of tables. So each of these objects in MLdp has a unique name, has independent permissions, has its own version, and the permissions and versioning are important because different teams can, for example, add their own annotations, and maybe that project is more secretive than the other project, and so needs to have restrictive permissions. And having independent versions allows each of the projects or each of the objects to iterate at their own cadence. And we see this is very common in machine learning organizations like Apple, where, for example, annotations often refresh far more frequently than the data set itself. And each version of your object, the data is immutable. So this ensures your reproducibility. Was there a question before?
I was versioning.
Okay. Yes?
What does immutable mean in this case?
Means the data can't change.
And how do you ensure that?
Ah, good. 4 slides. I will get to it in 4 slides. So how do we actually encode this conceptual data model into our system? So we have tables. So it's we have tables with a flexible schema. Here, the only thing we require is a primary key, and then we offer primary indexes. We offer a primary index using that primary key, but you can also specify secondary or partial indices. It's both, right? Yeah, this was a discussion I had today. I went with this, so good. I'm not totally wrong.
It doesn't have to be ES.
Does it?
ES or ICE?
See, I had ES before, and someone questioned me on it, and I took their suggestion. All right, good. So ES.
Question mark.
Just say indices.
Indices, everyone's okay with that? All right. So we're storing tables. Each of the columns in our tables can support a variety of formats. So scalar and collection types, and raw files. And in MLdp, we can either store them as byte streams in row or using off-row storage. The system makes that decision. We store our columns, or we store the table column-wise. This gives us efficient compression for each of the columns. And the way we spill off of main memory onto disk in how we've implemented our column-wise store. And of course, our tables are interoperable with other data frames that you're familiar with, so this makes it easy to get started, easy to start to use. So far we've talked about how I would turn that typical data set, that flowers data set, how that would be represented in a physical data model. But I haven't talked about in code, what does that look like? So let's go through what that would look like. And so for this example, I'll use a SQL variant domain-specific language that we've built in MLdp. We have a corresponding Python API because much of the machine learning community uses Python for their daily development. And so we have both. I'll use this as an example. So how do I create my flowers data set? I simply set the name and the primary key, the 2 required fields. I then specify what the sources are for each of the other columns. In this case, I want to have 3 columns: session ID, images, and settings. And then I specify the location on my local file system where the raw files are for this data set. And so just with that, I've got my data set created in MLdp. So let's go into how we're storing the data. So what's the storage system in MLdp look like? And at its core, it's a hybrid data store, starting with an in-flight data store, which is simply a distributed key value store. And this is designed for transactional workloads, high velocity changes. You can think of ingestion pipelines or annotation pipelines. And so the in-flight store is where data is coming in, and it's getting curated and refined and cleaned. And then it makes it over to the curated store. And the curated data store is read optimized. Versions of your data set are simply snapshots from the in-flight store. And all published versions are immutable. Yeah?
So when I'm doing the data ingestion, at that point, I'm only specifying this is the primary key, and this is the block that represents the rest of the object.
You can, that is sort of the minimum.
Okay.
You can also give more metadata. So you can arbitrarily choose what you'd like.
So if I already have 3 columns, I could specify that.
Yes.
So what format is the data ingested in?
So it's how would I say this? It's a variety of formats. You can tell us, so it's the.
Let's say this is CSV or JSON.
Correct.
Or any of those standards.
That's right. You can sort of say, so you can either say, I want this column as a JSON type, and here's where the contents of that JSON are. It's this set of files. It's this extension on the file system. Or you can say, I already have a data frame in as a Spark data frame or a Pandas data frame, ingest from that. So that's sort of the meaning. That's what I mean by interoperable. So it kind of works. The 2 views that we see most machine learning teams being very comfortable with is you've either done some work and already have a data frame, or you have a collection of files and you've organized your data set with some naming convention or some encoding in the directory and path structure that represents your data. Okay, so let's dive into this curated data store so I can get back to this the question that I didn't answer, which is how do we guarantee immutability? So how do we lay out data in the curated store? We start by separating or having data in local partitions. And here, you can provide a sort. It's optional, but we add a timestamp to ensure stability and to prevent data skew. The timestamp gives us sufficient entropy to split partitions on either heat or volume. Because we're using range-based partitions, we allow volumes to scale out without global shuffling. So now we take these logical partitions and we divide them into physical data blocks. These data blocks can have variable size. By keeping multiple blocks, we ensure that splits and merges are only happening on neighboring blocks, and that multiple dataset versions can share the same physical block. In fact, the way that we work on incremental changes, it's important to note that machine learning data tends to evolve in a really fractional sense. So if you have a 10 terabyte data set, the next version, only 1 gigabyte might change. And so we've adopted a copyright philosophy here to simply copy blocks that have taken changes. So how do we ensure immutability is that we don't allow we're pointing to the same blocks unless something changed in that block. The other reason that we use copy on write as opposed to a tombstone style mechanism for marking things that have changed or are no longer current is it gives us much more simplified bookkeeping for deletion. So when it's time to make sure that we can delete data, it's easier to do that. So this sort of gives you a picture of our overall storage architecture. We think there's a few things in this design that are tailored for machine learning. For one, we can exploit the partitions for data parallel workloads like distributed training. We can stream only the blocks that are needed on demand. And this is especially important, and I'll cover this in a little more detail in the next section in terms of how you consume data in MLdp. And because we have key ranges in our data blocks and an index, we can provide range scans and point queries. And these are both important things to do in both the exploration phase or exploration stage and the evaluation stage. So an example is if you're after you've trained your ML model, it's performing poorly, or it's not working with a particular example, you want to know what is the example that it's failing on. It's making a bad prediction. You've given it a picture of a flower and it thinks it's a cat. Why? So you want to load that example. That and that's a point query for us. Go ahead.
Whether the single point query and not kind of the bisection.
So we do single point queries at the record level, versus when you're saying a bisection, do you mean a part of a record?
Oh, because you have the outputs in the database as well, so you can just query for it. You don't have to rerun the model to figure out at which point did it change.
That's fair. Yes. Yeah. We don't have the output of the model per se in the database, but more that when you've generated the predictions, you know which examples it failed on. Where it was, so when you're evaluating, you have the ground truth in your test set. So you know the label was foo and you got bar for this example. So now you want to go and look at that example.
You have to rerun the model?
No, because you're not actually going back to the model. The model's already made its prediction and said it's the wrong thing. You want to go back to the data to say, what is this example? Why? What makes this example special? What
if I'm actually, I've developed my model, and then some user comes to me and says, actually last week we got this output. This week you're saying it's a dandelion instead of a rose. Yeah. In that case, I can't just query it because I don't have that customer's runs in the database. So in that case, I would have to rerun probably to find out where in which version it swapped. Right?
Yes. So there's a couple different elements there. One could be that the data skewed from the version you trained last week to the version this week, and then you would want to go back to you could look at the lineage or the changes in your in the versions of your data set to see how it changed. Yeah. So that would be one approach. The other approach is that you've actually changed your model architecture and your model is doing things differently, in which case that's often harder to do. But both are important ways to debug what happened in this situation.
The first step is figuring out where it changed or when. And that's not a point query, that's a bisection. Where you have to rerun the model.
Yes,
for that, or
yes, there is. It's outside of MLdp, but we have that infrastructure as part of the machine learning platform we have at Apple. So there's a subtlety in what you're saying. It's yes, we want to rerun the model, but you actually want to also understand were there changes in the model's architecture, in the code that was used for training the model. So this idea of you want this traceability back from, I have a trained model. What was the code that was used to train it? What was the data that was used when training? And what of those things has changed now from the last time? So you need the sort of the full artifact, a full ledger of all of these activities. And we have that. So MLdp contributes to part of that by knowing the versions of the data and ensuring immutability there, and by properly integrating with these with the experimentation and evaluation pieces of our platform, so that you can do that that type of debugging. Okay.
I have a question though.
Yeah.
Like this, I would say, is pretty standard architecture, right? Like because you're indicating it's ML tailored, but like if I think of all the other data parallel data management systems, they all store data, sharded horizontally. On each machine, it's going to be stored in columns, and all the columns will be also trunked into blocks, so that you only read the blocks you need. You can have indexing on top. So I would argue that this is pretty standard architecture.
I would not disagree, other than I think I guess one of the things that it's hard to one thing I think that we've paid some attention to is making sure that we are incredibly flexible and in not having strict requirements on how you set things up, so that we can work with a broad range of data formats and data types. And I think that how would I say it? It makes it easier to get started using our system with your existing pipeline, and it allows, I guess one way to say this is machine learning teams often have a very hard problem to solve. They're trying to I think the way I say it is they're trying to find a needle in a haystack, but don't know if they have the right haystack and don't know if there's a needle in it. So oftentimes if we can make our system natural for them to use, for those teams to be successful, then even if underneath our implementation looks pretty standard, we've still done something that's quite helpful. So I'll say before MLdp came in, before we built this, teams were storing their data in blob stores and were downloading their data with each of their runs and with each of their jobs. And so this, with MLdp, and maybe even the bigger concern was there was no element of reproducibility. And so there was a lot, there was no good way to know. Data was stored in a distributed file system. No one knows if someone changed something on that. So,
system, you basically don't have data management.
That's right. So
I think you're right. I think kind of the point is that maybe the basic storage architecture, you know, is based on key ideas, but the interface you want to on top of that, you want it to be tailored so that it's easy to support these machine learning workflows.
Yeah, I think that's great. Yeah, that's exactly the right way to think of it. It's so yes, that brings me to the last bit, which is how do I actually get to my data? So far, what have we done with this flowers project that we had? We modeled our data set. We created it using a DSL. We've now seen a little bit about how it's stored in MLdp. So how do I get to it? So for this, we rely on a streaming system. So we built so the way you access your data is you mount it. And we give you a file system abstraction, a file system view of your data. And the reason we do this, and so you can see we make this call. Here I'm using our Python API to go get my flowers data set and to mount it to my local file system at this path. The advantage of this is we can get started immediately. We don't actually have to download anything right away. We will do some prefetching. We'll use the local cache as an optimization, but you can get started right away. You can work on data sets much larger than your local disk. And this turns out to be one of those secrets of machine learning. A lot of it is happening on your laptop. So as much as people talk about machine learning happening in the cloud or in these big clusters, a lot of your work in those early stages of the life cycle are happening on your laptop. And so it's important that you can start working with the actual data set from the machine you have in front of you. And one thing we've seen is that this benefits us even in the cluster. So even when you're going for the large-scale experiment on the distributed cluster, you don't have to have each node in the cluster download parts of the data set they don't need. So by streaming the I/O, the cluster can get started quickly. So GPUs aren't sitting around idle, and these are critical resources that are shared in organizations, and there aren't enough GPUs for anyone. And so you don't want the GPUs sitting around idle. And so they can all get busy, they can all start working, and we see that this has a dramatic improvement on the wall clock time for completing a machine learning job.
Yeah. So I'm working on my laptop, and let's say I have my Jupyter notebook open, and I want to work with a data set that's in MLdp. Then I'm going to mount it this way. And once I mount it, then I'm going to do operations on these objects to actually get access to the data.
Yes. Yeah, exactly. That's and the other reason why streaming has been something that or this file system abstraction has been an important part of MLdp's design is that it allows us to integrate with all the ML frameworks automatically. Every machine learning framework knows how to read data off the file system. And so this way, we have this nice lowest common denominator way for every ML framework that's at use at Apple or that's available anywhere can immediately get started and take advantage of MLdp. And because MLdp is so flexible in that we just support any type of file, any format, you can actually use framework-generated data representations like TF records in TensorFlow or MXNet records in MXNet if those are interesting to you, and still take advantage of the streaming that's available. Go ahead.
Let's talk about how the file system abstraction to read data. How about after you train some machine learning model, how do you put data back to them?
Yeah, it's a good question. So I guess one way to think of it is one of the things we've seen with machine learning teams is the read-write pattern is so heavily skewed on the read side. So for every write, you're doing 1,000 reads. And so, so the write path does not have to be as optimized, which is why in the curated store, we're read optimized. This is exactly sort of the thinking behind it. Oftentimes, how would I say this? You care about the output of your model in the evaluation phase, but you may not need to store that back in how would I say it? The predictions are often not a data set for someone else. Sometimes they are. Sometimes you want to capture them back into MLdp, but oftentimes they're not. So I don't know if that makes sense. The shortest way to answer that is you can easily take the output of your model and follow that same DSL example I showed earlier for generating another object in MLdp, or adding another column to, like adding an annotation to your data set. Does that make sense? There was another question here.
Yes. So when you're training a model, you might want to have test and train, but
Yep.
within train, you want to have multiple splits.
Yeah.
Cross validation. Right?
Yeah.
So I'm just wondering about the versioning thing here. Every time you do different splits, are you creating a new version?
Yeah, you can. It's up to you. So the flexibility is yours. So what we've seen a lot of teams do is they'll create a split that does training, test, and validation. And they're like, everyone on the team, you're using this split. But then for your experiment, you may actually say, I want to take that split, and I'm going to do 5-fold cross-validation instead. So I'm just going to take the training data out. I'm only going to use that table from the team split, and I'm going to create my own split, which is 5-fold cross-validation, and I can use that. It often depends. So one of the ways to think of this is we often see machine learning teams doing, what's the right way to say it, like bake-offs. So there's 5 people on the team all working on the same problem, all trying to get the best model with the same split of the data. And then every 2 weeks, they want to see how close they're getting and who's winning.
I'm just thinking of complete version explosion happening here in terms of number of splits, number of people, and how much and the data itself is staying the same, and even if the annotations stay the same, it's just numbers. It can get
Yeah, I see what you're saying. There's a couple, so we offer, I didn't cover much of this, but there's a lot of just the generic metadata you'd expect. So all of the objects, you can have tags, description, title, there's a README that goes with all of them. They have independent permission, so you can say, look, my splits, I'm the only one that can see them. Nobody else can see them. So in that way, there's a lot of the sort of standard organization you'd expect from a catalog type of system.
And I can then search this catalog
Yeah.
and find an appropriate split. I don't have to
That's right.
create it.
That's right. Exactly.
Okay, thanks.
Yeah. These are great questions. And so this example is just a really cheesy one, but I'm scanning the local file system, and I'm doing, this is the computer vision library in Python to do things on this data set, the flowers data set. So this is how, in general, you access data. But the data is still living far away, right? The curated store could be far away from your compute. So the next thing we did in MLdp was build distributed cache clusters. And we deploy these co-located in each of the compute environments. So in this way, we bring the data closer to the compute. The advantages that we see with this cache is that it's transparent to the application. When you call that mount command that I showed in the previous slide, MLdp's backend is going to find the nearest cache and then tell your client to route all of its read traffic through that cache. The other part that's really great about our cache is that it's quite modular. So the thing that all machine learning teams want is consistent performance for their training jobs. And so teams can spin up their own Trove MLdp distributed cache, and that way make sure all of their data sets are always coming from the cache. So you get much more consistent performance. The caches that we have deployed that are co-located in the data center are shared for all jobs running in that data center. So if you want to ensure that all of your data comes from your cache, you deploy your own. Oh yeah, good question. So the cache, I guess the short way to say it is what's in the cache is logical key ranges. So it's it's the physical blocks around the ranges of keys that have been requested. So it's the tables and files in your data set.
Why did it need that? Isn't it just a database? So how does it help us speed computation?
Oh, sure. Well, so a lot of your data is not is stored. How would I say this? If your data set's 10 terabytes, it's not coming from a single database, right? It's coming from a collection of blob storage and a database. And so the cache allows, essentially, you don't have to go outside of your data center.
Is it also in memory or is it on disk?
It is both. So, so in the cache, we've designed the cache for large blocks, and we use both RAM and SSD. But I guess to answer your question more directly, it is simply an optimization. You don't need the cache, but you will pay, the latency is higher if you always have to go back to durable storage to pull blocks.
Oh, so this is just for pulling the data.
Yeah.
Having a cache in between.
Oh, that's, yeah, literally that. It's just the optimization of that.
Why didn't you just use the memcache or something?
Yes. Well, memcache only allows blocks up to 1 megabyte.
Or some other, there's no cache.
No, there's no caches that allow large blocks. We tried. We have no interest in reinventing the wheel.
Yeah, I guess it's a very simple caching problem because it's immutable.
It is immutable. We exploit the heck out of that. But the parts that are kind of interesting to us relate to some places we want to take this project going forward. But yes, the idea is we would love to have used an existing cache, but all the ones that we found couldn't support blocks that were big. And for machine learning data sets, the fragmentation, the blocks you want to work on are much, much bigger. And so the smallest we could get, the smallest we were willing to go was 16 megabytes.
What does AWS do in like their S3?
So there's, in terms of caching, like
because they have exactly the same thing, that the blocks are immutable.
Yes. Now, I don't know. It's been a long time since I was in AWS, so S3's probably changed a bunch. But they do, they have some tricks around making sure the requests go to the same pool of nodes, so that's one way to reduce the latency. So you're not actually going to the specific set of store nodes. You're going to that cluster, and that can, routing your traffic there can make it better. The short answer is AWS has no interest in, S3 doesn't need to be very fast. It needs to be highly available and durable. That's what its key value proposition is. You put something there, it will never go away. But in fact, AWS is pretty honest about S3 performance. If you're trying to get many small things, it's really, I mean, S3 API by itself is just, you can't do anything in batch. Everything is a full network call. It's a full REST API for every single request, for every single object. And so that you have to sort of think about that in how you're doing stuff. It's part of why we store things in blocks in the blob store that we use in the curated data store, is so that we are not going and pulling a single 2 megabyte JPEG off of storage. We are pulling a block around it.
So you're also doing the copy and write with that block size?
Yeah.
Or is that a different block size?
Block size we're using right now is, no, it's 256 megabytes is the block size we use in the curated store.
For copy and write?
Yeah.
So if just one bit changes, you just do 256
Megabytes.
megabytes.
Yeah. We have to think think in a much, much higher scale than that. We really have to think of a balancing act between how much wasted writes versus how many blocks do we want to manage. And so that was sort of the trade-off. And that's why having the blocks be 256 megabytes felt like a good fit. You could fit it into the working set. On fast networks, 256 megabytes will not take a long time to transfer, that sort of thing. That was why.
Did you experiment with different numbers there?
That comes from some, how would I say it, Ming Xuan on our team, the architect for the project, has some prior experience working at some large companies nearby that has done a lot of, that experimented with a lot of different sizes for this type of problem. So I mentioned we started this work about 2 years ago, and we have MLdp is in use today by many teams at Apple in their production setting, but there's more that we want to do. We want to make it easier to discover and explore your data. We want to add some system improvements around caching, prefetching, and we want to extend our DSL to better support data engineering pipelines. And finally, we want deeper integration with the ecosystem. Specifically, there are a few machine learning frameworks that are widely used at Apple, and we can provide a clearer or a better, deeper integration. One way to say that could be, let's say I want to go directly from the data to the GPU without having to go through the file system, the operating system, the user code, and then to the GPU. And we want to have better integration with annotation systems. So MLdp is a purpose-built machine learning data platform for data lifecycle management and workflow integration. Thank you.
Let's stop the streaming so we can take more questions.
Okay, I'm gonna, I think I go out of this.
Or you can just get up and talk.
I just have to switch to Chrome. Just give my laptop a second. Here we go. Now I can say stop and